Hello everyone. So in this session, let us look at real numbers. So before we go on to the details, let us learn some basics. First, what are natural numbers? Natural numbers, they are normally represented by n and they include 1, 2, 3 till infinity. Now, next, what are whole numbers? Whole numbers, usually represented by W, they have, in addition to the natural numbers, they have one more. It is just 0. 0, 1, 2, 3 till infinity. Now, next, integers. Integers represented by Z, and here what do we have? We have minus infinity, minus 3, minus 2, minus 1, 0, 1, 2, 3 on till infinity. So all of these come under integers. Now comes rational numbers. Now in rational numbers, usually represented by capital Q, they are of the form P by Q, where P and Q are integers and Q is not equal to 0. So what comes under that? All of these come under that, and you will also get numbers like 2 by 3. Yes, 2 is an integer, 3 is an integer, 2 by 3, and 3 is not equal to 0. So I have 2 by 3 is a rational number. Suppose minus 4 by 7. Very true, it's a rational number because both are integers and the denominator is not equal to 0. Now, these are rational numbers. Then I have another group called irrational numbers, which do not come under the form P by Q, where P and Q are integers and Q not equal to 0. So what comes under this? Values like root of 2, so root of any prime number, then value of pi. Value of pi, these numbers are, in all rational numbers, they will be non-terminating, non-repeating. If I write it in the decimal form, they will be non-terminating, non-repeating. Whereas rational numbers, they will be either terminating or they will be non-terminating, repeating. 1 by 3, 1 by 7, all of them, if you see, they will be non-terminating, repeating. So the set of the numbers that comes, that repeats after a while. Okay, but whereas here they will be non-terminating, non-repeating, like the value of pi. 22 by 7, this is a rational number. It is not irrational. Although you think that pi is equal to 22 by 7, the exact value of pi is not 22 by 7. It is an approximate value. So 22 by 7 is actually a rational number, because 22 and 7, they both are integers and 7 is not equal to 0. So all of these numbers, all of them can be represented in the real number line. So 1, 2, 3, 4, you have this 1, 2, 3, 4. On this side you have minus 1, minus 2, minus 3 and so on. But all of these numbers, you can represent it in the real number line. So I hope these are very basic things we have learned in earlier classes. So I hope you understand it. And now let's go on to some more details on this. Next, prime numbers. What are prime numbers? prime numbers are numbers which are divisible only by itself and 1. So you would think that, let's take 1, it is a prime number because it is divisible only by 1 and by itself, which is 1. But 1 is not considered to be a prime number. It's a special number. It's not considered to be a prime number. The primes start from 2. So 2, 3, 5, 7, 11, 13 and so on. Okay, so it goes on like this. So these are all prime numbers. You cannot break it down further. Now, composite numbers. What are composite numbers? Composite numbers are those numbers which can be written as a product of primes in a unique fashion. Suppose I have 42. How can I write it? I can write as 7 into 2 into 3. Or if I want to write it in order, so 2 into 3 into 7. I can write it like this. Suppose I have 24. How can I write it? 24 is nothing but 6 into 4. 4 can be further broken down as 2 into 2 and 6 is 3 into 2. So I can write it as 2 into 2 into 2 into 3, or I can write as 2 cube into 3. Now let us look at HCF. What is this term? It is highest common factor. Suppose I have two composite numbers or two numbers, which may one of them may be a prime also. In such cases, if two numbers are given, the highest common factor or both of them can be primes. If both of them are primes, the highest common factor would be 1. If you have two of these numbers, the highest common factor is the number which is a factor of both of these, and it must be the highest factor which can divide both of these. So let us see here, how do I find the HCF of 42 and 24? These are things we have studied in much lower classes, but let's just jog our memory. So 2 is a common one here. So what we should take is, we should take the 2 with the lower power. So 2 into, then we have 3 which is common. So we will take 3. Doesn't matter which one. So 3 is taken. So the high, and 7 is there only here. Here there is nothing. So basically it means 7 power 0. So the smaller one would be 1. So what you are doing is, you are taking 2 into 3, which is equal to 6. What about the LCM? LCM, take the same case. Which is the higher one? 2 power 3. So you would take that, 2 power 3 into, both are equal, so I will take that just as it is. Then, which is higher? Here there is nothing, so it is basically 7 power 0. This is 7 power 1. So I would take that 7, this over here. So then this becomes 6, 2 cube is 8 into 3 into 7. 7 3s are 21, and 21 into 8 is 168. So the LCM is 168. So these are things which we knew earlier, how to find the HCF and the LCM given two numbers. Or HCF, if you're given more numbers, the same process is to be used. Suppose now let's move on. After this, we are going to learn something called Euclids Division lemma, which we are going to use to find the HCF. But let us first look at what is this Euclids Division lemma. Before we go on and understand the Euclid's division lemma, let us see one very easy division that we can easily do. So 7 divided by 2. What do we get? 2 into 3 is 6 and the remainder is 1 here now. Can we do division further? No. Why? Because the remainder has become less than the divisor. So once this value becomes less than this, I can't do division any further. So what are the terms called? This 7 is called the dividend. And this 2 is called divisor. The 3 is quotient. And 1 is the remainder. This whole thing can be written in the form 7 equals 2 into 3 plus 1. So this is a concept which is used in Euclid's division lemma. So Euclid's division lemma states that, let me just clearly write it down, you can also take it down. For any two given positive integers a and b, there exists unique whole numbers Q and R such that there's no need to get worried about what all this English. It's very simple, just what we saw a little bit earlier, such that A equals B into Q plus R, where R is greater than or equal to 0, less than B. So if you see, we did this, right? 7, 2, 3s are 6, 1. So 7 is the A here, the B is the 2, and the Q is 3, and remainder R, that is 1. In this one, can be 0 when it is a perfect factor. It's a factor of this thing, it will become 0, remainder becomes 0. Or it can be greater than 0, but it cannot be, it will always be less than the divisor. That is, if it is 2, it cannot be 2 over here, it has to be 1. It can't be 2. So similarly, here, if it is being divided by B, the R has to be less than B. So this is what you need to remember. A is equal to BQ plus R, where R is greater than or equal to 0, less than B. Now using this Euclid's division lemma in a repeated fashion, which we call Euclid's division algorithm, we will find the HCF of two numbers. Let's do that. So let's do this. Using Euclid's division algorithm, find HCF of 1, 405 and 2520. So it is 405 and 2520. Let's see how we will do this. So whenever we get two numbers and we are asked using the Euclids Division algorithm to find the HCF, let us take A is equal to the bigger number 2520 in this case, and B is 405. So let's on one side keep doing division, and I'll take some more space. So 2520, so A is equal to 2520 and B is equal to 405. So 2520 divided by 405. So 405 into 6, 30, so 2430. So let's go to divided by multiplied by 6, and then you get 2430. What is left? 0 and 9. So 90 over here. You get 90. So I can write it. The first step, I took A is equal to this, B is equal to 405, and so it becomes 2520 equals 405, that is the B, into the Q, which is 6, plus R, which is 90. So this is the first step. Now in the second step, what needs to be done? Watch carefully what we are doing. So here this was the A, this was the B. Now in the next step, make the R as the B and the B as the A. So A becomes 405 and B is equal to 90. So 405, then the division 9 4s are 360, so 5 and you have, so 45. So it becomes 405 equals 90 into 4 plus 45. Now in the next step, again the same approach. The B becomes the A. So A is equal to 90 and B is equal to 45. So this is 90. So 45 2s are 90. So I can write it as 90 equals 45 into 2 plus what is left? 0. Now the remainder has become 0. Now at this stage we need to stop. We don't need to go further. Now what is the HCF in this? In the last step where the remainder is becoming 0, the B in that step is the HCF. So the HCF of 2520 and 405 is 45. I hope you have understood how we did this. It's a very easy process. So when you're doing it, show the steps here and by the side show the division, so that it's very clearly understood the way that you have gone about this. Now suppose you get three numbers and you're asked to find the HCF of that. First take any two numbers, using the Euclids Division algorithm, find the HCF. And after that, the second step, take that HCF and the third number and using the Euclids Division algorithm, again find the HCF. So I hope you understood. Please try out a few more problems which are there in your book, and in the next session I will be going on to do some more further areas in this. Thank you.